Hello, this is your Math 111C section 1.2 lecture. All right, so you know from just like, second grade, third grade, that if you have repeated addition, there are four of these. This is four groups of three. It's called multiplication. Yay. If you have three repeated multiplication, this is for 3 times 3. This is 3 times itself 4 times. Then it is written in exponential form. So we know that x, which is considered our base, multiplied together n times, is equal to x to the n. Further, because if I was to take n of these and multiply it by m of these, then this would be x to the n times x to the m. But if I just count up how many these are, it's x to the m plus n. So you can add exponents with the same base. Right? Likewise, if I divide them, let's just say if I have x to the 4th over x squared, those would cancel out with those. That would just be x squared. So in general form, that begs the question then, what happens when the top is smaller than the bottom and you have a negative exponent? And the answer is yes, you can. So just think of it this way. X is 1 time. X squared is x times x. X to the 3rd, x to the 4th. No. Imagine we go down. To get from here to here, I'm dividing by an x, taking 1 x away. Dividing by an x, taking 1 x away. Dividing by an x, taking 1 x away. So if I want to get here, I'd be taking this, dividing by an x, which is just 1. So x to the 0 equals 1, and that is true for any base. That's not 0. Okay. 0 to the 0 does not equal 1. It's an undetermined form. X to the 0 equals 1. All right. Now, so I have x to the 0 is 1. If I go down 1, I would be dividing 1 by x. You get that. If I go down 2, and we're dividing this by x. So you get this pattern, which basically says, voila. So if you want to write things without negative exponents, they move downstairs. What if I have a power to a power? What if I have 3 squared squared? That would be 3 times 3, 3 squared, squared, which is just 3 to the 4th. What about 3 cubed squared? That'd be 3 cubed times 3 cubed, which is 3 to the 6th. So we notice we're multiplying. So if you have a power raised to another power, you can multiply those 2 powers. All right. If you have something squared, the inverse function of that is to square root it. Okay. If you have something squared, the inverse function is to square root it. We're all relatively familiar with square roots. They are called radical functions. This is a radical. If you have something cubed, the inverse of that is to cube root it. If you have something to the 4th power, the inverse of that is to the 4th root it. Notationally, we can write this in exponential form by writing this to the 1/2. this to the 1/3, this to the 1/4. That is because we want these to be functional inverses of each other. That means if I take this and put it inside that as a function, which we'll talk a lot more about later, then I would get that, right? Multiply those two together. Likewise, of course, there are some domain restrictions here, which we'll talk about in the next section, but because you can't have negatives under even, you can't have negatives underneath even power radicals. They become complex numbers because you can't multiply something by itself that's negative an even number of times and get a negative number out. But as long as you're working within those domain restrictions, this is always true. Likewise, if I take 1/3, raise it to 3, raise it to the 1/3 power, that's x to the first, I just get x back out. A couple little rules. Let's say if I have this times this, I can put those underneath the same radicand. If I have this divided by this, it has to be the same radicand, then I can put those under the same radicand, right? All right, there's something called rationalized in a denominator. We always want our denominators to be whole, positive, and rational, WPR. So if it was like negative like this, we would write it as -1/2, right? Because our denominator is whole, positive, rational. Whole, positive, rational, right? So if I have something like this, and I want to rationalize it, first I recognize that I can write this as this. Yay me. If I multiply it by 1, but write 1 like this, so it doesn't change the value of this fraction because I'm multiplying the top and the bottom by the same thing. Now I'm going to have the square root of 80, 18 times 5 is 80, divided by, 18 times 5 is 90. Let's do that and make sure I did that right. 40, yep, 90. Whew, close one. Divided by 5, because the square root of 25 is 5. Now I can simplify this. There's a 9 in there, so this would be 3 root 10. Take the 9 out, the square root of 9 is 3. If we want to see that step a little bit slower, this is the square root of 9 times the square root of 10. Looking for perfect squared factors out of these. And this would be 3 root 10 over 5. Now I could leave this like this, which I think I will. Because I'm done. That's rationalized. All right. Whole, positive, rational. Try another example real quick of rationalizing one that has a sum on the bottom. All right. Now I would like to rationalize this denominator. I want it to be whole, positive, and rational. The thing is, I can't just multiply it by the square root of 3 because then I'll show you. Let's say, I'll get rid of the square root of 3 first. And I didn't put the square root of 3 times 3 when this multiplies into here because I have to distribute it, plus the root 6. You're like, okay, well now I'll multiply it by the square root of 6 and get the square root of 6 rid of. Now I'll multiply it in here, and I'll have the square root of 18 on top, and I'll have 3 root 6 on the bottom, plus 6, but now I still have a square root on the bottom. And I'd just be in this endless cycle of making this, equivalent fraction over and over and over again, always with the radical on the bottom. So if I want to get rid of this, I actually have to pull something out of my Algebra 2 class called the conjugate. And what that says, if I have any two numbers, a plus b, and I multiply them by their conjugate, which is a minus b, is the same binomial, two-term, with a different sign in the middle. Right? So if I multiply it by the conjugate, look what happens when I FOIL out a conjugate. First term, got to distribute the whole thing out. Minus AB, then plus AB, minus B squared. Look, the middle terms cancel out when I select them, and I end up with the difference of two squares, which is A squared minus B squared. That's why the conjugate is so special. Now I'm going to take this and multiply it, the top and bottom, by its conjugate. You'd be surprised how much we end up using this in calculus. It's a ton. It's a handy little trick, and it's good for a lot of things. So here we go, multiplying by the conjugate. The top stays the same. The bottom gets FOILed out, but because I multiplied it by the conjugate, I know how that's going to FOIL. It's going to FOIL the first thing squared minus the second thing squared. The first thing squared is root 3 minus the second thing squared. So I'm going to have root 3 minus root 2 on top, and on bottom, I'm going to have 3 minus 2. These cancel, those cancel. So I'm going to have root 3 minus root 2 all over 1, which is just root 3 minus root 2. Isn't that happy? Okay. Let's say I have 3 to the 2/3. What's that mean? That is 3 squared cube rooted, right? So it's 3 squared to the 1/3, which is the cube root of 9. What if I do it this way? This is 3 to the 1/3 squared, also equal to this. You can do it either way. This would be the root of 3, the third root of 3, whole thing squared. Right? So that's what those types of fractions mean. Remember that you just, if they have the same base, you can just add exponents. So the answer to this would be 3 2/3 plus negative 4/3, which would just be 3 to the negative 2/3. Remember, negative doesn't have anything to do with the base. It has to do with the reciprocal of the base. So this would be 1/3 from the negative raised to the 2/3, which I could also write as 1/9 raised to the 1/3. I wanted you to simplify it and write it with a positive exponent. So technically, this would work just fine, right? Or this one. Either of those answers would be good. All right, let's see. I think I'll let you go ahead and take a stab at this assignment. And please let me know if you have any questions. Put them in the discussion or drop me an email. Thanks. Bye.